Hello and welcome to this clip introducing bonding and how it's represented using dot and cross diagrams. We'll start with a brief review of the three types of bonding that you might have come across at GCSE and a mention of any major physical properties that these bring. We'll have a look at the basis for each type of bonding and how we can represent this using dot-cross diagrams before going on to look at some worked exam questions. And like we mentioned just now, it's assumed that you come across all the bonding types before at GCSE level. So covalent bonding is based on the sharing of electron pairs between atoms. So it's important to make sure that you get the definition right. It's the electrostatic attraction between a shared pair of electrons and the nuclei of the bonding atoms. It's not just a shared pair of electrons that was the old definition, but the new definition for the new specification for A level has to say the electrostatic attraction between a shared pair of electrons and the nuclei of the bonding atoms. And the electron density that this creates is said to be localized in the case of a covalent bond. So when the electrostatic attraction takes place between oppositely charged ions, we call this ionic bonding. So the important difference here is obviously we're not talking about sharing electrons. You actually end up getting an electron transferred completely from one atom to another. The atoms that lose electrons tend to be metals, and the atoms that gain electrons tend to be non-metals. This leads to the formation of a giant ionic lattice, shown in the diagram. There's actually no molecules in the lattice, so there's no NaCl molecules, for example. What you actually get is alternating positive and negative ions attracted to each other in all three directions, as now shown in the annotations. And if you were asked to draw an ionic lattice in an examination, you might do it like this. It's a simplified version and it has an element of 3 dimensions in it. So I've drawn an outline around it to show the 3 dimensions. You wouldn't have to do that. So ionic compounds tend to have some key properties. In red I've added a brief reason why each of those properties exist. So the details of these properties are covered in a separate clip, but this is just an introduction to them so you can see the kind of things that you'd be expected to talk about in an exam question, because there's many examples of long answer exam questions that require you to go into this in detail and show a true understanding of what's actually going on in terms of each structure. So it's very important to start to get an appreciation of this. So in metallic bonding you also get a giant metallic lattice. The difference here is that the electrons are delocalized, which essentially means that they're free to move throughout the 3D lattice structure. So if you're asked to draw a diagram showing metallic bonding, what you need to do is basically what's on the screen. But it's important that you have the electrons drawn as negative charges, and they're scattered fairly randomly throughout the structure to show the delocalization. It's really important that you have them labelled like is shown at the bottom of the diagram too, so the examiner knows what your pluses and your minuses are referring to. And if the metal ions are 2 plus or 3 plus, for example, don't forget to actually put 2 plus or 3 plus in on your diagram. Don't just put one single positive charge, because that makes the examiner think that you think it's 1 plus. So for example, magnesium is 2 plus and aluminium is 3 plus. So if they name a metal that you know has a 2 plus or a 3 plus charge, put the 2 plus or the 3 plus onto your metal ions in your diagram. So we've got 3 key properties to remember as well for metallic bonding or metallic structures. So the high physical strength and the high melting point are both down to the strong attractions between the positive metal ions and the delocalized electrons. In the case of melting, obviously the attractions have to be overcome completely. This requires energy due to their strength. With electricity conduction in both solid and molten state, it's the delocalized electrons. They're mobile and able to move and carry charge from one side to another. So if a positive terminal was attached at one side, the electrons would all be attracted towards it, and as they'd move, they'd carry charge along the structure of the metal. This is how wires in electrical systems work. So we use dot-cross diagrams to illustrate the distribution of electrons in bonds. So first of all, each atom has a slightly different representation for its outer shell electrons. We only draw the outer shell electrons, we don't do the inner shells because the inner shells don't get involved in bonding. And it's also very important the electrons are actually drawn on the circles representing the shells. As you can see in the chlorine, the crosses are actually drawn on the circle itself. And in the bond itself, the cross and the dot representing the bonding electrons, the shared electrons, are drawn inside the overlap, as shown. It's very important to get this bit right, because you can lose marks if you don't. So with double and triple bonds, they're handled the same way, but it's really important that the dots and crosses are alternated, as I've just highlighted, because each pair must represent one of the covalent bonds, which are also drawn in this illustration as the straight lines between atoms. So taking oxygen example, I've given you a correctly drawn and an incorrectly drawn example. And there are actually 3 mistakes, well 4 actually, if you include the fact that O wasn't drawn into one of the atoms. So these are all mistakes that we commonly see, possibly not all at the same time, but we see them quite regularly when we're marking work from students. So it's really important to make sure that when you do your dot-cross diagrams, you're precise and careful and neat about them, otherwise you will lose marks. So I'm going to set you a little challenge here. I want you to pause the video and I'd like you to draw these 2 diagrams out, and underneath each one try to say what's slightly strange about it. It may need you to go back to your original ideas you were taught at school when you first came across electrons and bonding. So in boron trifluoride, the boron atom only has 3 electrons in its outer shell of its own. So when it combines covalently with 3 fluorine atoms, this total is raised to 6, but it needs 8 electrons in its outer shell ideally, so this particular compound readily reacts further to try and gain those 2 extra electrons. So sulfur hexafluoride has 12 electrons in the outer shell of the sulfur atom. You'd normally expect it to have a total of 8. So what's happened is that the sulfur has made the d orbitals in its 3D subshell available, and what that means is that 6 covalent bonds can be accommodated now. This is called expansion of the octet, and it's commonly found in larger p-block atoms where they have 3D and 4D, for example, subshells, so there's room for this to take place. So here we have a quick look at dative covalent bonding. It's still the same situation. You still get shared electrons that are attracted electrostatically to the nuclei of the bonded atoms. So both electrons in the bond come from one of the bonded atoms. We have a couple of examples, H3O+ and NH4+. But these aren't the only examples of dative covalent bonds. In fact, there was one on the previous slide which we can look at in a second, boron trifluoride, or BF3. So remembering that boron only has 6 electrons in BF3, it's now got to react with an F- ion to try and pick up a further 2 to complete its outer shell somehow. So I'm just going to put in a couple of annotations to help explain what I've just done. So first of all, we have a dative covalent bond now formed between F- and the boron atom, which is highlighted in purple. The fluoride ion, you'll notice I've put a red electron in there, the 8th electron. Fluorine atoms only have 7 in their outer shell. If they pick up an extra electron by gaining it, they then become a fluoride ion. And I've actually drawn that in the fluoride ion there, so you can see that it's actually from somewhere else. So sometimes what we do in that situation, if you don't have the luxury of having 2 different coloured pens in an exam, is to actually draw in a slightly different shape. You might want to draw a square, or you might want to draw a triangle, for example, to represent the extra gained electron in the fluoride ion. So for example, a square or a triangle might suffice, just so the examiner can tell. There's actually 3 types of electrons involved. So it's also really important to get the correct definition for dative covalent bonding down, which is a shared pair of electrons in which the bonded pair has been provided by one of the bonding atoms. So you might want to get that down on a flashcard if you haven't done so already, because they may well ask you about this in an examination. So when we get ionic bonding, this is slightly different in that the electrons are transferred completely, and it leaves you an electrostatic attraction between positively and negatively charged ions. So you don't have to draw in arrows showing the electron transfer. This is just to illustrate what's going on between the 2 sodiums and the oxygen. But you do need to draw the oppositely charged ions close to each other to represent the electrostatic attraction. And you must show the electrons that have been gained being paired up with one of the electrons that are already there, as shown and highlighted in purple. And the reason for this is that it represents the gained electrons moving into partially filled orbitals in the negative ion. If you think back to your work recently on orbitals and how the orbitals get filled in subshells, looking at oxygen, you can see that it's got a 2p4 configuration. And I've highlighted the 2 partially filled orbitals. So those 2 spaces are where the 2 electrons are gained from the calcium. So the oxide ion is going to be a 2p6 configuration, isn't it? So the electrons that fill 2p5 and 2p6 are going to be the 2 electrons that it's picked up from the calcium. So let's have a look at some practice exam questions and see how you can put some of these ideas into your answers. So it asks me to draw a diagram to show the currently accepted model for metallic bonding. Now, obviously that one isn't complete. I've just drawn in the positively charged metal ions. It doesn't tell me which metal it's for, so I'm just going to put a single positive charge. I'm now going to add in my electrons, just at random, in amongst the positively charged ions. And I've put in a key to tell the examiner that I know what each of those things I've drawn actually means. So it says, what feature of this model allows metals to conduct electricity? So the conduction of electricity has to require the ability to carry charge. So the fact that the delocalised electrons can move means they can carry charge. So it's because the delocalised electrons are able to move around that this structure, this lattice, metals, giant metallic lattices in other words, can conduct electricity. So now let's move the page down a little bit. And it says fluorine has covalent bonding, and it asks you to state what is meant by covalent bond. So it's very important that you're specific here, and you say it's the electrostatic attraction between a shared pair of electrons and the nuclei of the bonded atoms. So drawing a dot and cross diagram, it tells us that we only have to show the outer electrons. So I start by drawing 2 circles representing the shells. I put the F symbol inside each to show it's fluorine I'm talking about, and I make sure there's a nice big overlap between them. And I put in a dot and a cross to show the covalent bond. And I pair up the remaining electrons on each atom to make sure that the examiner can see that I know that they're paired. So let's go on to the next part of the question, or the next question entirely. So it says limestone contains the ionic compound CaCO3, and it says it decomposes when it's heated strongly, forming an ionic compound, calcium oxide, and a covalent compound, carbon dioxide. It then asks you to state what we mean by ionic bonding. And as we know, it's electrostatic attraction between oppositely charged ions. So moving the page down a bit, it asks you to do dot and cross diagrams for calcium oxide and carbon dioxide. Now one is ionic and one is covalent. So I start off by drawing both ions in square brackets and putting the relevant charge next to each. Now I have to populate them with electrons. I have to be careful that I'm actually pairing the dots and the crosses up in the oxide ion like we talked about earlier. And the reason that the circle around the calcium ion is there because it represents the shell it lost 2 electrons from. You could actually just leave it out if you wanted. Sometimes people just leave out the circle. But if you do put the circle in, just make sure there's no crosses or dots on it. So when I'm setting up to do my dot cross diagram for carbon dioxide, look at how I've left a deliberately large overlap between the carbon and the oxygens to make room for the 2 pairs of electrons in each double bond. So a bit of forward planning is a good idea here. People often don't leave enough room and then stuff the electrons in and it looks like a mess. So to try and get around that problem, when you draw the shells before you put any electrons in, just make sure there's a nice big overlap between them. So I now draw my 2 double bonds nice and clearly with the dots and the crosses overlapping. And finally I pair up the remaining electrons in each oxygen's outer shell, because these are the electrons that are not involved in the bond. The next bit just asks you to do the electron configuration in terms of subshells for calcium in CaO. So this one's a little bit sneaky. Calcium in CaO is in the form of Ca2+, isn't it? We just know that because we've drawn it in the previous part of the answer. Tons of people get this question wrong because they go and draw the electron configuration for a calcium atom. It's a calcium 2+ ion, so it's lost 2 electrons. So what you actually need is 1s2, 2s2, 2p6, 3s2 and 3p6. So now let's have a look at the mark scheme. So we got our diagram correct, and we said the positive ions and we labelled them. We talked about electrons being able to move so charge can be carried. Now I just wanted to draw your attention to something here. This mark scheme is actually from a previous specification. Now all the other parts of the mark scheme are fine because I've double checked it before putting it in this clip. But just in case you were going to look at some past papers, for example, let's say you wanted to go and look on the exam board's website and you pulled up a past paper and didn't realise that it was from a previous specification, it might allow you to just say that a covalent bond is a shared pair of electrons. The new specification requires more detail. In other words, you need to say the electrostatic attraction between a shared pair of electrons and the nuclei of the bonded atoms. So this is a very important update. So this is what you'll find in your textbook, and on good websites it'll have done this update for you. But some websites may still be based on the old specification, so do be careful when you're looking at stuff online that you don't inadvertently pick up the wrong or insufficient definition for covalent bonding. So let's move the page down. And for the second part of that, it says correct dot and cross diagram. Now I took you through how to draw that, but I'll just draw it again here so you can see exactly what you need to put. So it'll be something along those lines. We said attraction between oppositely charged ions. I would advise against oppositely charged atoms, even though technically an ion is a charged atom. Just say oppositely charged ions. That's the safest way to do it. So the correct dot and cross for calcium oxide and for carbon dioxide, I need to bring the page down a bit to do that. So we've done the correct dot and cross, and we've done the correct charges. I put a tick next to the 2- to indicate that. And I've done the same for the carbon dioxide, giving me a correct dot and cross, 1 mark there. And I correctly worked out that a calcium 2+ ion is going to have a full p orbital. So it would be 1s2, 2s2, 2p6, 3s2, 3p6. So hopefully this has been a fairly useful video showing you how to update your dot cross diagrams from GCSE to A level. And if you've got any queries or questions, why not jot them down and bring them into your teacher, or have a chat to one of us on subject extension in college. And thanks for your time, and see you soon.